I was working in Antarctica years ago, and David Marchand worked with me, and that's what started the BU Antarctic program. I stopped working in Antarctica because of Wally. We went together in 1988 to the southern Andes, and we were worried about a problem, and I think the problem can be illustrated on this very simple diagram here that we put together for a paper in Scientific American. And what we were pondering is the following. The snow lines on the mountains in the northern and southern hemisphere are shown in red, and those are roughly at the LGM, is shown in blue. And what we couldn't understand is why in both polar hemispheres the snow line came down about the same. We could argue with the details, but about the same in both polar hemispheres at about the same time, and that it rose in both polar hemispheres at about the same time, not exactly the same time, but about the same time. We couldn't understand that because the prime hypothesis for what drove ice ages on Earth was the Milankovitch hypothesis, and that was namely that the summer intensity variations at around 65 degrees north somehow drove the great ice sheets of the north, and that in turn drove the climate of the world. That was the hypothesis in the 80s. And we said, well, gee, if that's the case, why does the southern hemisphere cool off? Because even by then, Suki Manabe was telling us that the expansion and contraction of the northern ice sheets are hardly felt in the southern hemisphere. So we began developing the idea of the possibility that the Earth's climate system preferred to be in one of two or three modes of operation. One we called the glacial mode, one we called the interglacial mode, and then we had several intermediate modes. And we suggested that the Earth had jumped between these modes. This is before we knew anything really about Darmstadt, Oskar, or Heinrich events. This is back in the 80s. And that one of these jumps was the end of the last ice age, and that it occurred in both hemispheres, and that it involved an ocean-atmosphere reorganization of the global climate system. And so we went to the southern hemisphere to have a look, to see if in fact, this diagram was true. We brought a number of people. Wally organized it, I didn't. He said, you've got to get out of Antarctica now, leave that to Dave and the others, and start working on the glaciation of the Andes and of South America. And let's come to grips with this problem. So I said, okay, it looks good to me, because I enjoyed that trip. We went all over the place. We went to the Beagle Channel, we went to Mendoza, we went to Aconcagua, we went to Isla Grande de Chiloé. We had a good time on that trip. We saw a lot of interesting things. And so I was hooked from that one trip. And he's the one who did it to me. And so we've been working together on this basic problem. And what I'm going to report is really just an overview of what we do. And it's these are joint projects between the University of Maine and Columbia with the field work. And we were helped greatly by a gentleman by the name of Gary Comer. Without him, I don't think we would have accomplished anything like what we have. Gary funded a lot of the students, the research, the Beryllium 10 lab, which in those days, Beryllium 10 was in its infancy, got Georg Schaefer to Lamont, and a lot of this is thanks to Gary, what we accomplished. So that's what the rationale was. Now, I want to just emphasize three puzzles. I don't know the answer to these puzzles. The Ice Age problem is one of the great mysteries of Earth sciences. We still haven't solved it. And so I want to indicate three puzzles which I think are coming closer to solving but haven't solved so far. The first occurred to me because in order to investigate this, I took a number of field trips to Switzerland with Professor Christian Schlichter of Bern, because I wanted to learn about the glacial history of the Alps, so we could compare it with the glacial history of the Andes at 45 degrees south, where the Milankovitch summer intensity forcing was out of phase with that in the north. And so one day Wally called me up and said, I need you down at Lamont on Friday. And I said, well, Wally, I'm sorry, I'm busy Friday. I can't come down to Lamont. And he got curious. He said, well, what are you doing? I said, I'm going to the Alps, and we're going to look around and take a look at all these deposits there. He said, where can I meet you? And I said, I thought you had something really important to do. He said, well, we might be able to do that some other time. And he came and he met us in Zurich, at the Zurich airport. We had a wonderful time looking around, and we scratched our head about some of the problems. And here's one of them. In Julia Pass, right there is a moraine which in Switzerland is called the Ägäisen moraine. They think it's Younger Dryas in age. I'm not so sure of that, but that's what they think. And you can see it right here. It's in Julio Pass, a high elevation, and the end of the present-day glacier is off to the right with a little Ice Age moraine there. And so we looked at the Ägäisen moraines, and we looked at the snow lines. You see, snow lines are very sensitive indicators of climate change. In fact, every time you hear about global warming, you hear about melting of glaciers and sea level rise. It's a very sensitive indicator of climate change. And shown here is a diagram of that red line represents the snow line rise at the end of the last glaciation. At the last glacial maximum, the snow line was 1,200 meters in the Alps lower than it is today, a little more than average in the northern hemisphere. And then it rose up, and right up there where it's red is the Ägäisen moraine. It represents a relatively small snow line lowering. And so I noticed that here and in the Austrian Alps and in Scandinavia, that the Ägäisen, or the Younger Dryas, called the Salposalki in Scandinavia, represented a fairly small climate change. And then Jeff Severinghaus, who was Wally's student, and everything Jeff says, I believe, because Jeff does everything with great care, he said the Younger Dryas climatic cooling in Greenland is 16 degrees Celsius colder than today. And I said, wow, there's something really wrong here. And I just read Moneyball, unfortunately, about Billy Beane, and Billy Beane looked for mismatches. And that's what I started to do, following Billy Beane's lead. At the time, the Red Sox hired him for a couple of days before he reneged on that. We would have had Billy Beane right across the street here if they had pulled that off. But here was a misfit. What Jeff said in Greenland was it was 16 degrees colder, and it isn't in Europe. Then we ran into Gary Comer, and Gary said to me one day, and we were up in Thunder Bay, George, you want to go to Greenland with me? I said, when? He said, this summer. I said, no way. I live in Maine in Boothbay Harbor, Southport Island. I'm not leaving there in the summer. I'll leave there in the winter and go to Antarctica, where it's much warmer than it is in Maine, but I will not go to Greenland in the summer. Well, Gary's persuasive, and I went to Greenland. I said, I'll go under one circumstance. Take what I want. I know where I want to go in Greenland. And he said, where do you want to go? I said, I want to go to Scoresby Sound. Because Scoresby Sound is the only place in Greenland where the moraine record, which we were looking at, was adjacent to the ice core record. And I want to look at this problem. And so we went to Scoresby Sound, and it didn't actually take a day to figure out the answer to this problem. The problem is as follows. Scoresby Sound is where it says Renland up there. There's a little ice core at Renland, and then inland, just inland from Renland, is Gibbs 2 and Grip ice cores. And this is what they were producing. You all know about this, the tremendously rapid climate changes of the last glaciation. The youngest of which is labeled YD here, is the Younger Dryas. And this is the isotopic record, but Jeff, using a clever method with several isotopes of nitrogen and argon, figured out the temperature change. And here's what I saw. I thought this had something to do with Greenland being unique, but what I saw where those cores were was a glacier, a little Ice Age moraine, which the Danes thought was AD 1500, and then right here, I saw the moraine, which we did exposure dating on, and it turns out to be either Younger Dryas or slightly older. And it's the same thing as in the Alps. And then the answer, what I think is the answer anyway, occurred to me. Glaciers are sensitive to summer temperatures. And Jeff was measuring mean annual. And if this was true, in order to have the mean annual 16 and the summer temperature, which ends up turning to be maybe 3 degrees colder, the winter had to change. And the only way that the winter could change was to ice over the North Atlantic, which would make the North Atlantic a Siberian climate with very cold winters. And on the left is a diagram Wally made to illustrate this, with it wasn't today's, 2004 sea ice and Younger Dryas winters. And Jeff made the one on the right that came from the fact that if the North Atlantic is iced over, and we think that that's because of that these changes are basically huge winter changes, because the North Atlantic is iced over. Well, in our little group we have John Chang of Berkeley and David Patisi of Washington became quite interested in this. So they modeled the effect of covering the North Atlantic with sea ice over in the rest of the northern hemisphere, and saw that the Earth's equator, the tropical rain belt, shifted south every time it was ice in the North Atlantic, And the monsoons, now there's debate about if it's monsoons or if it's slight hydrologic changes in the Andes, in the Himalayas, they changed too. And they were connected to the sea ice in the North Atlantic. And it became a winter phenomenon. So we suggested the seasonality was really important in understanding the Northern Hemisphere temperature record. I'll leave that and move on and come back to it at the end. Now, in order to understand Southern Hemisphere climate, these are the areas that we ended up working at in the Southern Hemisphere. CLD is a Chilean Lake District. I'll mention that in a moment. LA is Lago Argentino. CD is the Cordillera Darwin, the Antarctic Peninsula. We worked down the Transantarctic Mountains and in New Zealand. So those are the areas we covered, and they covered much of our field trip. We spent 10 years in the Andes, and I won't go into the details except to point out that the Andes had been mapped. The glacial geology had been mapped by Caldinius, a student of Yard de Year, and the map was published, and it's still a beautiful map, in 1932. And that map shows the extent of the Patagonian ice field, the last glacial maximum, with all of these moraines going right up. The bottom is Tierra del Fuego and Patagonia. I'll show you pictures of that in a moment, where ice emanating from Cordillera Darwin, which is right here, named after you know whom, he rode. The Beagle was anchored here. They couldn't row up the Beagle Channel because there's too much winds against, sail up because too much winds against them. So Darwin was rowed up the Beagle Channel, Mount Darwin, the Darwin Channel, the Darwin Mountains, and these lobes came out of the Darwin Mountains across Patagonia into the Atlantic Ocean. And there were lobes along the east side of the Andes, and on the west side, for most of the area of the Andes, the ice passed out to the sea, except at the uppermost part, the Chilean Lake District shown here. Now, the problem with working the Southern Hemisphere that not much had been done before we started. There were a few studies here and there, but not very much. And so we had to do all the mapping. And then the stratigraphic work, it just took a long time. Coring, pollen, took 10 years. That blue shows what the glaciers looked like at the last glacial maximum. And those numbers are some of our stratigraphic sections. And I won't bore you with them, except to say I hope you can accept that we actually could do it and could figure out what was going on there. It took us a while to do that. This is what the area looks like. It's just one example of a map. We had several people from Europe working with us, and that is Dave worked here too. I think I remember Dave, you there? Yep. There's that's the ice moraines of the last glacial maximum in red, the outwash plains out in front, the moraines of the last glaciation. And we had noticed that, and you will notice if you travel around the world, that inside this belt of LGM moraines, there are big lakes. This particular one is called Lago Yanquihue. That lake is 350 meters deep, and it goes below present-day sea level. These lakes are everywhere, and they represent something really important called the last glacial termination, the end of the last ice age, when ice evacuated these lakes. And the ice, what was filled with ice, is now filled with lake water. Here's a typical example of the moraines, and that view was taken looking that way. And this feature right here is that flat feature on the top. It's what we call a cane terrace. Now I won't go into, if you don't know cane terrace, you can look it up easily. It's a glacial deposit. And it's the youngest glacial deposit let down. And if we dated that glacial deposit, we found out that it was 18,000 years old. The last time the ice was in the LGM moraine belt, as we call it, was 18,000 years ago. And then the ice collapsed. We could put that in here this way. There's a stratigraphic section at the top with several of our workers, Claudio Ladore, whose father was a professor at Harvard at the time. Claudio is now a professor. We've left 5 professors behind in South America. I was traveling down to Cordillera Darwin last year with a friend of mine from Maine, and we landed at Santiago and stepped out for a little rest before we went down to Puerto Montt. And someone said, "Hello, George." It was Andre. And this guy said, do you know people here? I said, well, and then another one showed up at the airport. I don't know why, they didn't know I was there. And then I went to Punta Arenas, we landed there, and there was another one on the street there. And so this guy says, you know everyone in Chile? I said, I really don't. It's just an accident that they ran into me. But there were 5 of them teaching now at Chile and Católica. The upper one shows a stratigraphic section in the background. You can see a moraine, the organic material there. That moraine is 18,000 years old as well. And that was in the LGM moraine belt. But we knew, what we picked up right away, there was dramatic collapse right after that. And we picked that up for a lot of reasons, one of which is a pyroclastic flow that filled the area covered with glaciers at the LGM from Villarrica volcano. We could easily date that. And so the ice was at its maximum 18,000 30 years ago, and the endigmite was filling the glacial valleys by 16,900. There was a dramatic event that took part in this part of Chile. Now, when we put it all together, including the vegetation work, this is the scheme we got. There were a number of times when the glaciers were in the LGM moraine belt that I showed you in that red. Here, 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 and the last one at 18,000. A little over 18,000, and then bang, the ice went back. And we identified this tremendous collapse by that bar. And then Ulysses Ninnemann, who was then at Lamont and who is now in Bergen, worked in the core just offshore from Lago Yanquihue, and that's his record from Boloides. And he thought the glacial sequence lasted right through here. And then he found the same rapid collapse in here back to the Holocene positions. Now, to me, this was a little reminiscent of what we've been talking about, these mode flips, a flip from a glacial climate to an interglacial climate, but it's one place, it might be an accident. So we moved down to Cordillera Darwin, which I pointed out to you before. And at Cordillera Darwin, we used a boat of a neighbor of mine by the name of Charles. Have any of you been to Yosemite Park? Have you seen El Capitan? The first solo ascents of all the hardest routes in El Capitan were made by this fellow back in the early 70s. And he's my neighbor in Maine, and he's a little different than from most people, but still, what's that?
A lot different.
Okay, he's a lot different from other people, but he's a dear, dear friend of mine. And he does happen to have a 70-foot catch. And if you want to read about him, Google him in the New York Times. He died last February. His name is Charles Porter. New York Times ran almost a full-page obituary about him. But Charlie has a boat that we chartered. And we were in this area that Darwin worked in for months at a time. And what we did was we started at the outer part. You see that part that says 18.3 and Bahia Unantil, that's the last moraine deposited in the LGM moraine belt, and it gave us the same age as the last moraine up further north in Chiloé. And that's the moraine, if you can make it out, with the boulders on the moraine. And by that time, we finished in the Chilean Lake District. Jörg Schaefer had worked out all the bugs, not all, you never work out all, but most of the bugs in beryllium 10 dating, and they were giving spectacular ages. And so we're able to date these moraines now. This is one of the boulders on the moraine, and that moraine gave an age of 18,300. Then with Charlie, we went to the heart of Cordillera Darwin on the boat. Can I shut these lights down a little bit? But oh yeah, we sailed up the Beagle Channel, and we came to this fantastic fjord called Pia. I don't know if any of you have been there, but Pia Fjord is an incredible place. So we sailed into Pia Fjord. We worked at Pia for a while and came up here, and we anchored the boat right there. Now, you see this little neck right here where you come in? There's a swarm of dolphins in that neck that gave us a lot of trouble because every time we took the Zodiac in and out of there, dolphins chased us. And we could only put one person on the Zodiac with Charlie, because if we had two people on, the Zodiac was slower than the dolphins. And they catch us, and they had a heck of a good time splashing us, all the way in and all the way out. And the water's cold. And so that was the danger here, the dolphins. And from here, from here, we looked at this ridge. You see this ridge rising right up toward present-day snow line, and we collected rocks and organic samples from that ridge. That ridge is in the heart of Cordillera Darwin. Now, that's what it looks like on the ridge. The weather's usually awful. There are bogs in depressions. That's an aerially scoured ridge, which means there are bogs in the depression, but there are beautiful rocks, perched rocks around the bogs. And so we could get ages using the rocks and using the organic material from the base of the bog to get minimum limiting ages on the deglaciation. And lo and behold, if they weren't the same as we got up in the northern part of the former Patagonian ice field in the Chilean Lake District. That ridge was deglaciated by about 16,800 years ago, almost the same age that we got up north. And we also did the ages of the boulders. There's a boulder right beside one of the bogs in the back, and you can see the weather here. It just pours all the time. And the rocks we found that ridge gave us an average age, about plus minus 400, 17.3.
How do you date when the boulder rested there?
We date when the boulder rested there by sampling off the top of it and seeing how many beryllium-10 atoms have been produced by basically cosmic rays entering the top, because of spallation it produces beryllium-10. It's a spectacular new method. It's not so new, it's been around for about 30 years, but it's been developed to a high art now. For example, Aaron Putnam, working in the Tian Shan, working on the Little Ice Age moraines, which generally thought to be 1850, got an age of 1854 plus or minus 2 using this method. That's what it looks like now. Okay, so both these methods indicated rapid deglaciation of Cordillera Darwin. So all of a sudden, the change from these outer moraines again, bang, gone, fast. Those are the two ages combined, the yellow being the rocks and the red being the organic material. Okay? Now another group, which had a former student of mine also, Tom Davis, who teaches at Bentley now, worked just north of Ushuaia in an outer piece of Cordillera Darwin, and they found the same thing. Tucked way back in the mountains, right outside a moraine deposited during what's called the Antarctic cold reversal, are boulders just outside that gave ages of 16.8 and 16.9. So the evidence was accumulating that there was a very rapid deglaciation beginning at very close to 17,700 years ago and over with fast. To my mind, it began to look like a mode flip taking place then. So to check that, we moved to New Zealand, and I've never left. Once I got to New Zealand, I decided, I don't know what I'm doing here, but whatever it is, it's going to take me a long time. It took us actually 9 years in New Zealand to make the maps. The maps have been published by what used to be the New Zealand Geological Survey. It's now called GNS Science, some fancy name. But it's still the Geological Survey because a former classmate mate of mine at Yale was in charge of that. And they never work with outsiders, except when I went up to see Ian, told him what we were doing, he made an exception. And so we worked with the survey. And they did all the digitizing of our maps. We have a tremendous layout of maps of the entire Southern Alps, on which we could carry out our beryllium-10 exposure age dating. And we could work there with the glaciologists, particularly those in New Zealand, but we worked with 3 different glaciological modeling groups. And the strategy was to do the glaciological mapping, and then to apply the beryllium-10 age dating on the moraines that resulted from the mapping, and then to work with glaciological modelers to figure out what all this meant. And we had 3 different groups that were developing glaciological models and studying the glaciers in New Zealand to see what temperature change and even a little bit precipitation, but it was mainly temperature change, was necessary below today's value to drive the glaciers to these various moraines, which we were dating using beryllium-10. Here's a view of New Zealand's Alps, and again the red represents the moraine systems around the edges of the lakes, which would look very similar to Iago Yankiwe here, Tekapo, and these others. And out in front of that, this yellow scheme showed the outwash plains deposited by streams flowing from these glaciers. The maps are done 1 to 50,000, just take my word. I'm really proud of these maps, but no one else is. I mean, you all look at citation indexes. If you want to get a low citation index, spend 10 years mapping the moraines in New Zealand, 5 digitizers working for 3 years to digitize it, put it out in a monograph, and maybe 10.
Nobody reads.
Nobody reads. Looks at the maps. But I love them nevertheless. That's my thing. George Schaefer's thing, and it was to do the dating, but my thing was the mapping, and so we could get along just fine. The white up on top shows the present day, the glaciers in the Alps. Okay, here's an example. This is an example of what we did with a key person here is Aaron Putnam. He's taken over all this. I'm in the rearview mirror. I don't do much now except applaud from the sidelines, but there's the map. And here are the dates we have on the map. You're looking at 5 years of work right there on one map. Here's the dates on the last glacial advance. 1805, 1803, 1808, 1804, 1806, 1801, 1801, 1802, 1802. Same thing we found over across the ocean.
Probably don't have enough data.
You may be right. I have to go back again. In fact, I am going back again. January 7th, I touched down at Christchurch Airport again. Now, it's fantastic there because there's a little tectonic movement in New Zealand, and on the left lateral side of this moraine sequence, it uplifts just slightly, which means the moraines are uplifted one above the other, just slightly. And so and this is what it looks like. At dawn, over the Southern Alps, that's Mount Cook in the background. Can you see this moraine set here? These are fantastic climate records. Moraine set here, here, here. It goes right up on the hill, one after another after another. We started to work there, but we ran into a problem. Peter Jackson was working there too at the time we were working. He was working right in the moraine we're interested in. This moraine turns out to be 20,000 years old, and he was filming The Hobbit right there. And he snagged our glaciologist working with us. And he was puzzled. He couldn't understand. He said, all my friends try to become extras in The Hobbit, and Peter Jackson just turns them away. But he just saw me, and he took me, and I said, I can't help you there, Trevor. I don't know what he saw that he needed you, he needed you in The Hobbit. I can't help you out there. It wouldn't occur to me why that happened. So Trevor was absent part of the time, but let me show you this. If that's our moraine. The dwarfs are here, defending themselves. There's the wizard. And that's our key rock. That's the moraine, 20,000. Those are the types of boulders on the moraine. And that's what we could obtain the ages of the moraines from using this technique of beryllium 10 age dating. And the moraine that the wizard said, over here, you fools! We ran over and collected from the top. And it turned out to be 20,000 years old, that moraine did. And the wizard rode across the same helicopter as we did. He had to take off his pointed cap going over. That's what the moraine looks like. And here's some dates on those moraine sequences. The youngest one gives us that 18,000 date again. Then the next one averages 20,000. Then the next one, 27,000. And then the next one, 35,000. Then the next one, 42,000. And it will continue on. It goes up there. The stage 4, the 65,000 is there as well. And so we tried it in that part of the moraine sequence, and we noticed something. That when we plotted the ages of the moraines here, in these camel plot diagrams, they had a pattern that seemed familiar from working in Greenland and with those winter events in Greenland. Now, that is, the pattern of these moraines was such that they fell between what are called Heinrich events. Heinrich events are those particularly cold winters in Greenland. There are Dansgaardska events and Heinrich events. And these moraines fell between Heinrich events. And the massive recession from Pukaki, as well as from Yankiwe, fell right during what's called Heinrich Stadial 1, the Heinrich Stadial 1 event. But I wasn't sure whether to believe this, so we did it 3 times. I won't bore you with all 3 times, but the next time down, there's some more of the dates that we put up together there. Then we put all 3 together, we get consistent results. There were moraines at 18.4, 17.9, 19.9 here, 20.4 here, 20.4, 28, 27.6, 27.6, 36.2, 35.3, 41.8, 40. Within the realm of geology and moraine dating, that's pretty good. And so there we had it, and they fell between Heinrich events. And then Aaron, he's got to do things in much more detail than we do. This is his, not mine, and Toby Kaufman's, who's now at Lamont as well. We went to the big valley, Rakaya Valley, and that's where Lord of the Rings was filmed, in Rakaya Valley here. But they weren't there when we were there. And we dated all these features. Now, the mapping of this took 3 years, and then all this exposure dating. Now, the only thing I'm showing you here, I'll let those who did it show it in more detail, but working with, it turned out that Anne Rowan was doing her PhD in glaciology there. So we worked with her group here, and we worked with other groups in Pukaki. And the idea is that the glaciological model could be tuned to fit every single moraine and would give us roughly the climate change necessary to produce a glacier at those moraines. For example, the moraines at Reichert Knob would be 2.25 degrees Celsius below today's. The one at Double Hill, 4 degrees, and the LGM was 6.25 degrees Celsius below today. Now, these large lakes that I mentioned before, I showed you Yankiwe, these deep, large lakes, they represent something. They represent a collapse of ice at the end of the last glaciation. Here, right there, is the moraine dated at 20,000. And then right there is the outer edge of the moraine dated to 18,000. And then after 18,000, actually beginning at 17.8, the ice disappeared. Something like this. 300 years of glacial retreat, it's just gone. Right back to the late glacial moraines. It was just like we saw in Pukaki. It was fast. Well, we double-checked this, we triple-checked it. This is a student who just finished at Lamont. These are just hot off the accelerator at Lawrence Livermore. And there is in all these positions a late glacial moraine set that's equivalent to the Antarctic cold reversal. So the ice at the LGM moraine, bang, back to the late glacial, in behind the late glacial moraine, the late glacial advance, and then another slight recession. No need to go through this in detail, but we just repeated it. So we were fairly confident about it. And so if we put it all together, it looks something like this. From the north, these H1, H0, 2, 3, 4 are the Heinrich events from a number, in this particular case, from the Chinese stalagmites. And the moraines fell between them. Ice was oscillating in here, and then boom, right there. The same retreat that we saw in the Chilean Lake District. And that retreat was over with fast. Okay, keep that in mind, and I'll come back to it just for a second near the end. That's our pattern that we found, both in New Zealand and South America. Then we attacked the third problem I mentioned, which is sea level. Now, when I look out the window here, if I worked at BU, I'd be a little nervous myself. That's the Charles out there. There's not very much lower than, we're on the second floor, so we're okay here. But BU is on made ground. BU was on soils dug out from Beacon Hill years ago, which is a drumlin. And there is a debate in climate change as to whether the Antarctic ice sheet, which is a great potential source of sea level change, undergoes millennial instabilities, the greatest of which is called meltwater pulse 1A. And there are many attributions that meltwater pulse 1A is partly fed from Antarctica, with a sea level rise attributed to Antarctica of 7 meters in less than a few centuries. We investigated that too in our Antarctic work. Now, what we did was to look in Antarctica at the largest drainage system. Brenda Hall's taken over most of this. I started it. No, that's in the rearview mirror for me. Dave worked on a little bit of it too. This is the largest drainage system, that drainage system that flows ice from East Antarctica and West Antarctica into the Ross Embayment. Now, notice this red is the Ross Ice Shelf, and it's anchored right here on one side in a promontory called Minna Bluff and Ross Island. And the other side is anchored against in King Edward VII land. And it's anchored on a little bit on Roosevelt Island right here. So there are two anchors to the Ross Ice Shelf, and there are ice streams feeding into it. In this area, at the last glacial maximum, what happened is this grounded, and there was thickening of outlet glaciers. But there was one place where the outlet glaciers didn't thicken, and ice curled around up into McMurdo Sound and flowed westward and impinged on the land of McMurdo Sound. And it looked like this. Came into McMurdo Sound and impinged. This was a shock to us when we started working in Antarctica. We were working in ice-free valleys, which were just off the biggest ice sheet on Earth. And we didn't see any ice coming down the valleys. We saw ice coming in out of the sea. And the ice in the valleys had retreated at that time. We could tell that easily from the geomorphic relationships of the moraines. We couldn't figure this out. It took us about 10 years to figure that out. The ice came in and left a spectacular moraine along the coastal part of the Transantarctic Mountains. That's what the moraine looks like from a helicopter view at 2 in the morning. Well, you see it there? It's not subtle. You can see it from space. Now, the ice that impinged on the Transantarctic Mountains, trapped between the ice and the side of the mountains were little ponds. And the ponds are fed by a little teeny bit of meltwater coming off the ice, and the ponds are filled with algae. And material fell off the ice into the ponds and buried the algae. And so when we get radiocarbon dates of the algae, we're actually getting radiocarbon dates of the building up of the moraine. Okay? So it looks a little bit like that, but I won't go into the details. And here is that moraine. And it's beautiful all along the coast. Dave Marchand helped me map the flow directions across McMurdo Sound years and years and years and years ago. Now Brenda Hall is working on it, and she's dating the algae. There's the moraine, and there are some of her dates. She has about 150 now on that moraine. And those are the dates. So every date represents a piece of algae being deposited in the moraine. In order to date the whole thing, we have to get 100 dates, so we cover the whole thing. And when that happens, all the dates fall in this interval between 13,000 and 18,000 something, almost 19,000 years ago. We think the ice was at its maximum through that time. And that the recession of the ice didn't begin until 13,000 years ago. Now Brenda, working with John Stone, has been mapping the outlet. I mapped one of them. I mapped the Beardmore Glacier one, but they've mapped Reedy Glacier and Scott Glacier. And what happens, and these outlet glaciers that come from the East Antarctic ice sheet through the Transantarctic Mountains, is when grounding takes place in the Ross Sea area, it dams up these outlet glaciers. All right? So they look like this. They rotate. They have a fulcrum at the top, and the bottom spins up, and the top hardly moves. It's all because of grounding in the Ross Sea. And then alongside the mountain front, there are erratics left behind, perched all over the mountain front of the Transantarctic Mountains. You can see this one here? It's even what we call a perched erratic. It's got a little one underneath. Another one here. Exposure age dating of those indicates that the ice was at its thickest about 14,000 years ago there, and then slowly went down in the Transantarctic Mountains. And so that's what it looks like. Slowly comes down from 11,000 down to the present day 340. And so we did that for the Scott and for the Beardmore here, mountain area, got the same results. And so all three areas that we've done age dating on, in this indicates, doesn't show evidence of a meltwater pulse 1A, which is supposed to be 14,700 years ago. So we can't find any evidence of millennial scale variability on this largest of the sections in Antarctica. And what we think happens is this. We think that this is a new curve from Antarctica with the temperature at the top, and that's the accumulation. It's published now, it's not in press. What we think happens is that the ice sheet grounds, probably because of sea level lowering and decreased melting at the base when accumulation is low, and then when the climate warms up, for what we see in New Zealand when ice collapses and the climate warms, you can see here that on the right side of the red, the accumulation doubles. And so we think there's a sweet spot for every part of Antarctica where this LGM configuration has an additional ice thickness added to it from the increased accumulation. And then after that, the marine influence of rising sea level and increasing melt under the ice sheet causes downdraw and inland migration, and the ice begins to retreat. So every place in Antarctica has a different LGM age. The LGM of Taylor Glacier, which drains East Antarctica into the dry valleys but does not connect it to the sea, is right now. It's now at its maximum. The LGM for the dry valleys area, there I showed you, McMurdo area, is between 13 and 18. Further south, it's 14, and further on top of the glaciers, it's 8. Now, there's been a long debate. I remember when I was with Terry Hughes back in 1978 or so, we worried about Pine Island Bay and Thwaites Glacier. They could collapse. And he wrote quickly, with one finger the way he typed, wrote a letter to Journal of Glaciology, which got published and is now very famous. It's called the weak underbelly. He didn't call it soft underbelly, the weak underbelly of the West Antarctic ice sheet. And in Science in July came out a study that this marine ice sheet, unstable, is underway. Whether it is or not, I can't judge, but that came out in Science. And then we wondered about why this one here didn't show any rapid variability. And I think it has to do with the fact that our geological data indicate that the Ross Ice Shelf caught on this pinning point 8,000 years ago and has been there ever since. And I think it's that pinning point that holds together the Ross embayment. And so that the future of ice in the Ross embayment depends on the solidity of that pinning point to Minna Bluff. Now, I will conclude with this. I still wonder if what we're not looking at in the southern hemisphere is a mode flip, we used to call a mode flip. That there was a glacial mode. This is one of the slides I showed at the beginning, right here. Glacial conditions, and then interglacial conditions. And there's the transient condition, the mode flip. Because every place I look there are sets of moraines out at the edge of the lakes, then nothing except way at the head. And that nothing takes place at the same time. And it lasts at the most 1,500 years. Well, I speculate, I just wonder if, since we can now tie, what would cause this? If the Earth's in one mode, what jolts it into the other mode? And I think that a good candidate is the Heinrich Stadial II event from the north, because it correlates exactly with this jump. And we know from the geological data and from John Chang's work and others that the far field effects of Heinrich Stadial I were dramatic. Earth's thermal equator went south, the monsoons, wind belts. Wally's shown the ocean changes its circulation pattern. The whole atmosphere ocean changes its circulation pattern. So I can't help but just wonder, I don't know if this is right or not, but the Earth is in one stable mode in a glaciation, and then these Heinrich events keep hitting it, and they hit it 3 or 4 times, and they cause a little warming in the south, then it dies back down. It doesn't quite do it. And then the final Heinrich event does it, and one could say, well, why does the final Heinrich event does it? And I would just speculate it does it because the ice sheets in the north are at their maximum extent. The last termination always occurs when the ice sheets in the north are at their maximum extent. So I would put it together to suggest that there are, in fact, modes of climate change, and that they're jolted from one mode to the other by these big punches called Heinrich stadials that hit in the south, and everything changes in that mode switch. Carbon dioxide changes, and if carbon dioxide changes, the water vapor must change, and the atmospheric circulation changes from a glacial to an interglacial mode. That's speculation, but that's what it looks like to me from the geological record. And with that, I'll leave you in peace.